Who here, I imagine, who here likes to be right? Right? Who here actually thinks they're right? Right? Okay, we all work in SRE, I think, or around SRE, and we're used to being a little bit right and a little bit wrong. Today, we're gonna talk about how we do that, and I'm gonna tell you a specific story, how we were a little less wrong over multi-years about a really big problem that we had. So first, to mention a little bit of who I am, biggest bullet point here is I'm an incident nerd. I can't resist. If there's an incident, I have to dive in. It's kind of a sickness, and my good friend and co-host Colette knows how to pull me out of that. But I just have a really big head for nerd snipes. So that's what led to a lot of what we have today. I'm also a tech lead for a production engineering team. What that means is we just are the team that they bring all the weird stuff to. Production isn't the way we expected it, so go ask production engineering. We also own things that everybody shares in production, so it's basically a platform team, like the databases and the queues and things like that. I host a podcast where we talk about how people actually have to do this work. And most importantly, I'm just me. I don't speak for my employer, who I won't mention right now, so that we can talk freely about this story that was inspired by true events. But what are we really going to talk about? I heard somebody mention yesterday global learning and local learning. So we're going to have a global learning and we're going to have some local learning. The global learning that I want you to take away today is that while we're doing site reliability engineering, we need to be doing a little bit of site reliability science. We have to have a little bit of rigor as we look at these systems, and if we don't, we're just going to keep spinning all the time. So I'm going to tell you a little story, but the names, places, times, dates, everything have been changed to protect the innocent. That's me. And I also do know that that's a medic and not a scientist. But I just like how the scientist is sort of like wide-eyed, looking to the future, and the engineer is just like, oh, I got to do this work. And the local learning that we're going to have is about Postgres, multi-transaction locks. Can I just get a hint? Does anybody know how they work? Okay, I was going to call you a liar. Anybody like work on Postgres like deeply, like? Okay, great. So I can tell you lies. So what Postgres multi-transaction locks are is sometimes when you're in a database with multi-version concurrency, you need to have things not disappear. That's really all it is. So in this example, we got a schema where like these many-to-many related objects also have a foreign key back to this like ancestor object for reasons. In this case, there's like a chance that the many-to-many relationship will get lost and we'll have orphans. So we want to make sure we know who owns that ultimately so we can clean it up someday. And by doing that foreign key in this specific database schema, we created a problem, which is we insert millions and millions and millions of these child objects. And when we do that, we have to share lock that one tenant object all the way at the top. No matter how many concurrent threads are going, they all have to share that object, and they have to make sure it doesn't disappear. Sub-transactions also need to do this, but we're not going to get into why that is. How does it do that? It's crazy. Like, I wish I could do the next, I got 31 minutes left. I want to do 32 minutes on this, but you're all going to go to sleep. The really important things to know is it's a bunch of 32-bit integers that just get written to disk. In the database, there's header fields that define what the oldest and newest transactions are, and those are constantly moving as the versions change. In each table header, there's these things called frozen transactions and frozen multi-transaction locks that get kept track of by the vacuum process. In the rows, you have just that row. When did it get born? That's xmin. And when did it get deleted? Xmax, except asterisk. If the flags say that that's actually a multi-transaction lock, then that's not when it's deleted. There's this offset file that has all these 32-bit integers saying this multi-transaction ID is over here in this member file. And then the members file is just a bunch of transaction IDs. Why does all this have to exist? When you're in a multi-version concurrency system, you have to be able to tell if something is visible. Because it may be about to change, or it may have changed from the time you started your transaction. This is all just background. Put it in the back of your mind. This is how things have to work. But now let's get into the fun stuff. This is a story. This happened years before I joined this production engineering team. And I only know about this because they wrote stuff down and made good incident reports. So please write stuff down, put them in incident reports that won't die. I found this graph early on in this investigation. Basically, they were trying to solve a minor problem in the hot path. So you see that nice little line over there. It was like taking 10 milliseconds. They're like, we need it to take 1 millisecond. And so let's make an index. It's a good idea. They were like, there's a better cardinality index. Let's make it. They made it, and it totally improved the query until several minutes later, something reverse improved it. So the engineer who was doing this was just watching this query's performance. They were like, I just made the index, and now things are better. And then just as they were about to like disengage, they saw this graph go up, and they didn't really panic. They just were like, uh-oh, something bad is happening to my query. I should run a vacuum analyze. The graph on the top is not the query's performance. That's the entire database's performance after the vacuum analyze was run. Panic ensues, right? What did I do? Everybody's pagers go off. This is a big monolithic application with a big Aurora Postgres database that has to be up, and now it's orders of magnitude slower, and no one knows why. So they sort of look at the system, they're twisting it around, they're trying to figure out what's going on. Finally, the engineer, after several minutes, is like, what if we just drop the index? They drop the index, and everything goes green. Now, this is a weird position to be in if you've ever been in this situation. The engineer's like, I took actions. I have causal effect on this database. I can see it in the graphs. I did this, and this happened. And so if they did just traditional root cause analysis, they wrote this down as a root cause. An engineer created an index on the table, which led to global latency problems. The problem was resolved when the index was dropped. That's a root cause. Okay, we can tell the customers that. But why? Like, why? What does that actually tell you about the system? What was actually happening? While they were analyzing it, they noted a bunch of stuff that they just didn't know. They were like, why were all these threads in this LW lock MultiXact waiting threads mode? This team doesn't have Postgres core developers on it. Like, what the heck is that? They also looked back through the logs, and they actually found in the metrics, and they found that like every day, sometimes multiple times a day, a little graph like the one at the bottom happens, which is this little mohawk would like build up of these waiters and then just drop, and build up and drop. And in this case, if you look at the previous one, that mohawk was just much bigger. Why? So the team kind of had to move on because they're not scientists, they're site reliability engineers. So they had fixed the system, they moved on, but they did write down a hypothesis. MultiXacts are bad. That's all they had. They're like, okay, well, let's watch for them. And the only experiment they could really run in this case was just watch for those wait states, see if they can correlate with failure modes. Hypothesis 1 confirmed. This one actually was confirmed. Yeah, so it looks like MultiXacts are bad. What you see here are the graphs of long-running transactions. Whenever you start a transaction, that graph starts going up, and when it finishes, that graph goes down. And these were found to correlate exactly with those wait states, but not always. Sometimes a long-running transaction doesn't make the wait states happen, and sometimes the wait states don't make it happen. So we could be looking at cause or effect, we could be looking at symptoms, but we do have a confirmation. MultiXacts are involved in something bad. They needed a new hypothesis. So they decided, let's assume long-running transactions are preventing the auto-vacuum process in a Postgres database from cleaning out those multi-transaction locks. That would cause them to build up in the system. If you go back to our thing, like, why do you need multi-transaction locks? Well, we have to keep a list of all the transactions that are currently running that have a lock on the table, but with Postgres, we can't ever really like clear those out until we run vacuum. So every time we encounter that row, we have to go back and look at that list and see if any of those transactions are still running. And so auto vacuum comes along and just, it freezes them. It marks them as like, those aren't active anymore. And so they're building up faster and faster. And when there's a long running transaction, auto vacuum can't touch any of those transactions. That's the hypothesis. So the experiment they came up with was, whenever we see those wait states, we're just gonna kill the longest running transactions because that should work. They actually kind of got some data here over the next year. There were some of these similar lockups and latency bumps. Every time, they just were like, kill the longest running transaction, that'll work. Until it didn't. So fast forward, we're about 2 years after that initial latency event. And we get this. If you can't see, it's kind of hard to see because the graph just looks empty. On the right side, you have like many more orders of magnitude of growth all of a sudden in a really alarming pattern. Those are the locks on all the tables in the system. Doesn't work very well when all the things are locked. To the runbook, right? They had written down their experiment basically as a runbook, and I think we do that as SREs. We're like, we need to run this and learn things from it. And so they had written down this awesome query, and everybody had access to it. It was linked to in the alerts about the locks. Run this, and all shall work. Except transactions stopped stopping. By the way, I love this AI-generated image. This is a database running a stop sign. We live in a strange time. But essentially, what happened, normally this would work. It would just kill the longest running. But the problem was the longest running transactions were in this weird state. LW lock, MultiXact, offset SLRU. What does that mean? Somewhere, some developer stuck that into a state and said, someone will understand this someday. They looked in the code, they're like, I don't know what this means. It's all this weird concurrency stuff. The team is in time pressure here. We're now in hours of incident time, hours of downtime. And the usual, they would call it bailing water out of the leaking boat, just wasn't working. So they needed a bigger bucket, or as they called it, they did the nuclear option, which is just turn it all off and turn it back on again. Everything's all green. Like instantly, everything comes back. Everything is fine for 10 minutes. Not great, not great. So it was just long enough to shut down the incident bridge and have everybody like disengage, but immediately like people come back in the incident Slack channel like, there's something wrong, and everybody's pagers go off again. Goes right back into the same state. If this graph right here is those MultiXact offset control locks that you saw before, the team is back into panic mode. What do? You go back to hypotheses. Now that original hypothesis is out the door. The long-running transactions obviously weren't the problem. They just, 1,000 hypotheses bloomed. Some of the ones that came up a lot were, there's an audit log system and it seems like there were a lot of inserts there. Maybe that's a problem. Except that's like a compliance issue. We can't turn that off. Vacuums on these like high churn tables seem to be eating up a lot of IO bandwidth, but there wasn't any known ceiling for the IO bandwidth for this system. So they turned it off, but it's not healthy. So that doesn't work. Low priority jobs could be interfering. This system has a lot of like background cleanup of really complex relational tables. They turned that off, but that wasn't going yet. So the system was just completely unhealthy. They said, well, what if we turned it off and back on again? And everything goes green. You feel it? You feel it? This time it was for about 24 hours. Not a good time to be on call for this system. Panic ensues again. This is the next day now. And actually, for the next 8 days, it happened 4 times. Now, this is where resilience comes in. The team figures it out. Like, they make this work. They just start, like, watching the dashboard. Does anybody here watch the dashboard? Yeah, yeah, yeah. I found out I'm my company's #1 observability user because they're like, what do you do? I'm like, I just refresh this dashboard a lot. And that's what happens. And they start to see a leading indicator, but it's not a great leading indicator. 5 minutes. You got 5 minutes from when this number starts to jump up, sort of, I wouldn't say exponentially, but fast. If you go ahead and just redeploy the app really fast. And they found faster ways to redeploy it. So instead of going through like the whole CI/CD pipeline, they figured out they could just like go into the container orchestrator and turn it off and back on faster. They got to the point where there wasn't downtime, but there was still like this dangerously bad effect happening, and they don't have any idea what's going on. Obviously, Hypothesis 2, out the window. Even with no long-running transactions, the system is locking up. So they come up with another one. They're like, okay, I think we see that the number of multi-transaction locks being generated, that's the problem. And it's just overwhelming the DB in some way. So remember, we've already confirmed MultiXacts are bad. So having lots of them is worse. So we should generate fewer of them. So let's do an experiment. Let's just go on a tear reducing these, right? We don't need all those foreign keys, especially on like high churn tables. We could maybe try to introduce concurrency limits so we don't insert too many child rows under a single shared thing. All of this happens in development in a number of days, while there's otherwise an actual global code freeze going on because people are scared that the system isn't going to come back and be reliable anymore. So that's their experiment, and their expected rate result, no more lockups. That's an expensive experiment, especially when we're already in debt with our error budget. We're way below water on our error budget, and we're running an expensive experiment where our confirmation of our hypothesis would take an undefined amount of time. So the biggest problem, though, was there actually wasn't a measure known to the team for how many MultiXacts were even being generated. So they were just sort of going on vibes, like, we'll see it again or we won't. We saw it again. And unfortunately, just a couple of weeks after all of this effort was done, the database did fill up with locks. We did see like a slight improvement, but ultimately the wait states came back. They tried like pausing all that low priority work, nothing, okay? But the only thing was turn it off and back on, and they got really good at turning it off and back on. At this point, the team realized they needed to become better experts. This isn't acceptable, essentially. Like, we need better understanding of Postgres. It's a busy SRE team. They hadn't really built their expertise on this. They were just sort of trusting that Aurora Postgres would do its thing. And that became a key point. They leaned out on Amazon support, and they leaned out onto other experts, and they found a lot of blog posts about the fact that Aurora Postgres is actually special. It doesn't have an OS VFS cache layer, and because it doesn't have that, cache misses when reading multi-transaction locks are really expensive, and the buffer size has to be increased for it to perform, except we're 4 major versions behind, and we can't even see it. So, huge hypothesis. I am so sorry to try and make you read it. I won't. But essentially what it says is all that stuff I just said is causing the problem, we think. And if we can just measure the hit rate and watch it, we can find out what's driving it up. We can sort of look at what happens before and prevent that. So the experiment is upgrade 4 major releases, not an easy task. If anybody done an upgrade of a major release of Postgres? It's like downtime, difficulty, things break. They get it done, and they start to see, actually, this is good. This is less wrong. And that's a great result. But this site reliability scientist, this SRE was like nervous. Like, I know the database isn't going down anymore, but like that hit rate goes all the way down all the time, and we still don't go down. There's like sort of doubts, but you move on. There's no fire to put out. So the team moves on, and a whole entire year So that year goes by, the database is beautiful. We're good. We start to build up some error budget. And so I wore the shirt today. We decided to test in prod and not live a lie. We've been running load tests, and we say, it's time, we're going to push prod. We think we know that if that hit rate drops, we'll stop the test, we'll back it out, right? Traffic to 500% of normal, no problem. 2% drop in hit rate. It's beautiful, everything is going great, till it's not. A few minutes later, anybody? This is what happens. So it looked okay, but then this is a different graph. This is the aggregate reads and writes to the SRU caches. These are these caches that sit between the system and those files on disk that have all those 32-bit integers. And they go up a lot. So normal was near 0. It would maybe spike to 100 or 200. We're in the millions now, folks. And if you recognize a quadratic growth curve, that's what you see there. Eventually, it does actually flatten out because we're essentially in a dead state. We've reached the capacity of the system to touch the disk. But obviously this is bad. Open transactions are stuck. We have found the maximum number of open transactions we could do, 4,000. We found the maximum number of locks. There's a lot of data here, but the system is down. And in fact, what happened, I'll back up a little bit. There were actually 2 incidents. So the load test happens, and we're able to recover it quickly. Turn it off, turn it back on again. Still works. Great. But a couple weeks later, it happened again. Nothing was happening on the system. It was actually pretty disorienting. We had had a year with no events, and there was no load test going on, and it goes back to dying. We couldn't figure out why. But we noticed something. If you look at that arrow on the right, 1 million became the new normal for the next 2 weeks. The thing was doing 1 million SRU aggregate accesses all the time, whereas before the load test had been none. This was new learning. This was an aha moment. There's pressure that stays in the system. Even after you've cleared and turned off and turned back on everything, something is still sitting on disk, making your life terrible. And in fact, the event several weeks later was a long-ish running transaction. So we're back to this old chestnut. We've got old long-running transactions, and we've got this pressure in the system building up. Now we're really learning. We've done the work, we've done the science, we've gotten enough. So hypothesis 4 is out. Even though that model got us an entire year of peace, we had to let go of it. Because we found this was great learning. Hit rate doesn't matter. I mean, hit rate probably matters in some scenarios, not for us. The most important thing that we learned that day was we need to find out what does matter. And we did. It's that aggregate number. So hypothesis 5 was born. Aggregate MultiXact cache pressure can increase to the point where it overwhelms the system's ability to read rows with MultiXacts on them. Vacuum freeze relieves the pressure by freezing old MultiXacts, removing the need to look up their XID members. What does that mean? I'm deep in the weeds, y'all. Help. This is where we live now, actually. But our experiment was let's set the alert level at 200,000 per second. And remember that new normal was 1 million, so we tried to give ourselves a little space. I will say we created an alert fatigue generator at that point. The thing went over that threshold constantly. I want to apologize to Reed on my team, who was on call that first week. It was rough. But those alerts taught us. So we'd get an alert, we would run vacuum freeze, and the system would stay in total stasis. In fact, we didn't have any downtime during that time. And in fact, the database has not gone down since then. Did anybody have the dashboard? Can I look at it? I don't think it's down right now because we do have this model, but we did create this sort of mechanical Turk. Aggregate pressure's building up, pull the lever. So after a couple weeks, Reed, in anger, discovered that there's actually an answer for this. Auto vacuum has this setting. Auto vacuum multi-exact max freeze age. What does that mean? One of the things about multi-transaction lock IDs is they have an age. There's a distance between when they were created and now. And as that grows, it's more likely that you can get rid of that multi-transaction lock. And so the system by default at 400 million will vacuum that away. It will freeze that, meaning it'll mark it as this couldn't possibly be running right now, so you don't have to worry about it. The only reason they set it at 400 million, and this is in the comments in the code, thank you for comments in the code, Postgres developers, is because it's a 32-bit integer. It wraps. So 400 million gives enough time for the vacuum to finish before it will wrap around if you're on a high transaction system. We didn't have a wraparound problem. We weren't even coming anywhere near that age. We were running at like 7 or 8 million. But setting it to 1.5 million seemed reasonable. Like, cool, we run at 8, let's keep it down below 1.5 million. Wholly auto vacuum. This doesn't make sense, I'll try to explain it. The top was a normal day before that setting. We would get little spikes where auto vacuum would like loop 1,000 times in an hour. We are now running like 40,000 an hour, maybe 50,000 an hour. Auto vacuum is just constantly just like obsessed with our tables, just vacuuming and vacuuming and vacuuming. And we got a little nervous, but the system doesn't go down. It's kind of great. And we wouldn't have known to do this if we didn't do all this science. So I'm still kind of wrong about this. We're still kind of wrong about this. Hypothesis 5 probably will be invalidated someday. We actually have this weird, sick need for the system to go down, so we find out new stuff. I don't want it to go down. Don't tell my bosses I said that. But I don't know any other way to do it. We've done load tests, and it just doesn't work the same without the production traffic. We can't break it in staging. It doesn't break. Put it in the test harness and it'll go to 1 billion. It's the user activity and the entropy that's coming from the users that's doing it, which is why we want to do this science some more, but we can't until it breaks. So don't break database, but break a little. So yeah, what's hypothesis 6 looking like? I'm not sure. I have all these questions. Our team has these questions. Why? Sometimes when we run a manual vacuum freeze, instead of letting auto vacuum do it, it does way, way better. No idea why. Talked to many Postgres developers, AWS support people, nobody, they're like, I don't know. It's weird. Postgres is weird. Multi-transaction locks. Actually, if you want to not make friends at a Postgres conference, talk about multi-transaction locks. They're not happy about it. We still don't really know why we have so many multi-transaction locks. We know foreign keys make them, but they have enough value that we're going to keep them. We know sub-transactions might do them. We still don't know why. The system is stable, so we're not allocating any of our excess budget to find out. Also, Postgres 17 did this cool thing where they made that cache work better, presumably because other people had problems like this. Maybe that's why we're not going down too. Also, are we just wasting I/O? I/O isn't free on Aurora Postgres. No idea. So I want to leave you with this. Please, 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 I said this in the beginning and I'll say it again. Snap the graph and put it somewhere where it won't die. So we can have talks like this. Write things down. Write down what happened in the incident. I know you've got your postmortem form. It says, how did we get lucky? And why, or you're doing your 5 whys. Whatever your company needs you to do to file that document, I understand. But please also, if you don't understand what happened, spend just a little more time to write down your questions. Make a hypothesis. Do a detailed incident analysis and share it with people and try to teach people about it, because that's the only way you're going to get through some hard things like this. Also, just don't be afraid to be a little wrong. Make a statement in a hypothesis that this probably isn't right, but if it's a little bit right and a little wrong, that'll help us learn. And One of the things that you might have caught in here that I think is important, and I really didn't even understand this until I went back through this whole sequence of events, your error budget really can drive whether or not you're able to learn. In the early stages, we were underwater. We couldn't really do the learning, and we had to pay with pain and more downtime. We actually had to double down and go even deeper into error debt. But when we had enough, it took a lot of pushing to say, no, we're gonna actually burn some of that error budget to learn. Like, I'm not gonna lie, some people still are a little unhappy that we just made an incident happen in production. But those of us who understand that the next 6 months of peace came from that, no, you've got to spend that error budget. That's all I have, folks. Thank you.